Yeah, so we were talking about proof systems with quantifiers, and I'm going to continue that. Last time we saw the famous Gödel completeness theorem. So this is the Hilbert system, the where you have the propositional axioms and then axioms for equality. Which is x equals x, and t equals t prime implies alpha of t is equivalent to alpha of t prime. This is the notation, but actually what we have in mind, and that's how I prefer it, is alpha equivalent to alpha prime, where alpha prime is got from alpha or t prime for t in some places. And this is important because you don't have to uniformly replace, right? The substitution of equals for equals you can carry out everywhere, anywhere. Remember in school, this is what you do, right? LHS and RHS, you find substitutions, you find equivalent expressions, you substitute them anywhere. So that's the, and this is the, with these two axioms, you can derive whatever you need, especially to show that the equality is a congruence in the completeness proof. And then quantifier axioms. So this is for all x alpha implies where t is substitutable for x in alpha, and alpha implies for all x alpha when x has no free occurrence in alpha. If x is not occurring free, alpha will imply for all x alpha, and then distributivity for all x alpha implies beta implies. Yeah, and as we saw, all these are actually used to derive something which is fairly innocuous, but which is really bound variable renaming, right? To derive this, we used all the three axioms, and from that, then we actually show that whenever gamma derives alpha with x replaced by y, where y is nu, then yeah, this is the generalization from constants but written for variables, and that's it. And with that, we can actually do the completeness proof. So, well, last time I went through it, I mean, the Gödel completeness theorem is a big thing, but I thought since we had already seen the proof of the compactness theorem in some detail, and it's pretty much the same argument, everything repeated wherever we were doing for FinSat, you are repeating it with consistent. And now, of course, you have to show derivations, and that's it. With this, the whole thing goes through. Okay, and the only different way that I did it was that rather than expanding the language and working with constants and so on, you can simply use variables, right? So for witness fulfillment, you just make sure that if there exists x alpha belongs to gamma, then alpha with x replaced by y belongs to gamma, where this is a new variable. How do you ensure that new variables are available? You start with whatever given consistent gamma, rename all your variables so that you have countably many variables available, and do that. And you have to show that that is consistent, where a little bit of trickery is involved, but then everything goes through smoothly. So this was the message of last time, and so this proves the completeness of this system. And but as I said, Hilbert systems doing proofs is always a problem, And with quantifiers, of course, it's even more of a mess. What I want to show you is to how we would take up all these things with natural deduction and sequent calculus, and also resolution, which is, these are the things that we did for propositional logic. So I want to show how quantifiers, how all these proof systems work with quantifiers. With resolution, towards the end of that lecture, I talked about how you do it with quantifiers, but I'm sure that was, it was just a zip through, so we'll do it a little more slowly. Because that's a fairly interesting and important thing, and normally not discussed much in mathematical logic, but for automatic theorem proving, that's perhaps the most important engine. Okay, so let's look at natural deduction first. What are the rules for natural deduction? You have introduction rules and elimination rules. Yeah. Natural deduction. And what are the introduction rules? And introduction, if you've got alpha, beta, you can get alpha and beta. And elimination 1 and elimination 2, right? Fairly obvious. And then for disjunction, you have 2 disjunction introduction rules. Not alpha, of course, but beta. And then disjunction elimination is slightly weird. If you have alpha or beta, from assuming alpha, if you can derive gamma, assuming beta, if you can derive gamma, then you can derive gamma. Yeah, this is the disjunction elimination in natural deduction. And like I said, you think of this as case analysis. Consider the case where beta is not alpha. You say either alpha holds or negation alpha holds. In the first case, I show gamma, and in the second case, I show gamma. So in all the cases, gamma holds therefore. Right? This is the justification for that. And of course, all these rules are sound. Implication introduction. Well, if you assume alpha and derive beta, then you can derive alpha and beta, discharging assumption alpha. You make an assumption and you discharge it by introducing implication. And implication elimination is the same as modus ponens. If you've got alpha implies beta, whenever you have derived alpha, you can also derive beta. So that's the, and then you have negation. So negation introduction, negation elimination, maybe I can write it here. What is negation introduction? Well, I don't even remember in what form I did it. If from assuming alpha I get beta, and assuming alpha I get not beta, then I can have not alpha. Not elimination, assuming not alpha, I get beta. Assuming not alpha, I get not beta. Then I can. Basically, once this is the reductio, ready? Reductio ad absurdum. Assuming alpha, if I can get a contradiction, I can get negation alpha. Assuming a negation alpha, if I get a contradiction, I get alpha. Yeah. So that's negation introduction, negation elimination. So these are all the rules that we have seen. Now, what about quantifiers? So quantifiers, of course, you will have a for all introduction and for all elimination. There exists introduction and there exists elimination. Yeah. So how do we expect this to go? Yeah. So what would be for all introduction rule? If you want, I'll write the quantifier axioms to remind you. What were the quantifier axioms in Hilbert style? Alpha implies for all x alpha where alpha has and then now the third one is really a thing with the Hilbert system, right? Because you've got a Hilbert system and your modus ponens is only your inference rule, you're writing it in implicational form, you have to have some way of doing this, really, right? This is an instance of, because you are having the Hilbert system, you are having axioms, you have to write it. Otherwise, you don't really need this when you are working with inference rules. If you remember, I also talked about having this as an inference rule, right? This you could have as an inference rule, right? Because you remember in proofs we always allow generalizations, right? I hope you remember this that we talked about, that the notion of proof in a Hilbert system with quantifiers is that axioms are schemas. Everywhere you can take substitutional instances in proofs, and you can throw in any number of universal quantifiers, right? And that's because if alpha is valid, of course for all x alpha is valid as well, right? I hope that's clear. Yeah. And therefore you can also have rules like this. In fact, this is a weaker rule and it's very interesting to use this rule instead of generalization, right? And this axiom is capturing precisely that. But this is where all the work is being done, and I hope you can see that this is basically a case of for all introduction and for all elimination, right? That's what is going on. So can you guess what the for all introduction and for all elimination rules would be? Can somebody tell me what would be a for all elimination rule? Well, for an elimination rule, what is the structure of an elimination rule? What should be on top and what should be below? Ananya, can you help me out? Right, so let's write for all x alpha. So what should be the thing below? Exactly, not some variable. Which particular variable? We are eliminating for all x. So alpha with, that's it. Huh? I mean, it has to be this. That's my point, right? You don't have, this is the thing about natural deduction, right? You have to eliminate the quantifier. How do you eliminate the quantifier? By choosing an instance. If you have shown that for all x alpha is a valid formula, right? And this is the point. If it is a valid formula, then you can substitute any term for it. But what kind of terms can we substitute? We know that, where t is whatever. Yeah? If t is, we know this business, right? We went through this in painful detail in semantics. Assume this is valid. Suppose this is not valid. There is a particular model, right? There is a particular model which makes it false. Now, because t is substitutable for x and alpha, I can transfer it to the left hand side. You know that in that model, in that model, look at the valuation for x with whatever pi hat of t, alpha is not true in that model. But then we have been told that for all x alpha is valid, right? Therefore, for all x alpha is true in that model, and that's a contradiction. Yeah. So this is the for all elimination. What about for all introduction? Again, there is not much choice. How will for all x introduction look?
For all x alpha should be the bottom at alpha.
but there is a condition here. So what should we have?
Hello?
Yes?
That x is not free in alpha?
X should not be free in alpha. But so now natural deduction is usually stated in a slightly different form, and you will see why. And so this is how it is. You could do with terms. Let me not do it with terms. Terms is more complicated. You have to worry about other variables and so on. But let me just choose a constant symbol, right? So let C be a constant. You have this provided C does not occur in alpha or in any that's a side condition. This is basically our proposition of generalization from constants. You remember what was the generalization from constants? I just went through this. If gamma where C is nu, then yeah, remember that this is the one that we got all the paisa vasool for, right? This proposition, and that's the form in which it is used because you can directly use it, right? So you don't have to worry about free variables and so on. This includes the case where x is occurring free. I am not worried about it, right? Yes, Swapnil, you get the point, right? You could have. This is an axiom. What is the difference between axioms and rules? This is a very important thing to understand. Axiom says it's valid. Take any model. If the model makes the left hand side true, that particular model will make this is all operating within a single model. When you have inference rules, you are saying if this is valid, if this is true in all models, this is true in all models. You are not relating it in a single model, right? It's of course, if you can relate it in a single model, you can relate it in across models also. That's a much stronger condition there. So this is the main duality from between axioms and inference rules. And here, since we have this proposition, right? And what is this idea of this being new? This being new means it's not used in alpha anywhere, and it is not used in gamma, any of the assumptions. But as far as natural deduction is concerned, which are the assumptions that you must worry about? The undischarged assumptions, right? They are the active assumptions. Any assumption that has been discharged, you have converted it into an implication anyway. So who cares? So this is the proof theoretic analog of the crucial lemma that I keep coming back to, right? Generalization from constants, or in the form that I stated last time, which is generalization from new variables, right? New syntactic elements, right? And that's the spirit of the universal quantifier. And once you understand that, you can do proofs very, very well. And usually this is what is not well understood. So many authors for symmetry would write with C, then you don't have to worry about t being substitutable for x and alpha and so on. Remember, a constant is always substitutable, right? So you don't have to write it. So they'll just write this. Okay. So this is typically the form in which natural deduction is stated. Okay. Is it clear? Ananya?
Yes.
Yeah. Okay, no problem. Yeah. So now, if this is clear, let's look at what will be the rules for existential quantifier. There exists introduction. Yeah, somebody? And there exists elimination. Okay, maybe let's take this up later. There exists introduction should be very straightforward, right? I want to conclude there exists x alpha. When can I conclude there exists x alpha?
Sir,
Yeah?
when x is substituted by.
That's it. Here there is no condition, nothing. If you have shown alpha with x replaced by some element, some constant, then surely you can write that x alpha, right? Is it clear? Right. Now what about there exists elimination? How do you eliminate an existential quantifier? You got there exists x alpha above the line. How do you expect to get rid of it? I want alpha below. This sounds like a fairly impossible thing, right? I mean, from a universal quantifier, you can specialize, no problem. But from an existential quantifier, how can we?
X is not a free variable.
Well, that's true. You can do it in that case, but it's pretty useless, no? In that case, Gayatri, suppose I write some there exists x px, and then I want to go get rid of the existential quantifier. You are not helping me. Okay, remember semantically, what is the relation between conjunction and the universal quantifier? You can think of the universal quantifier as a kind of a giant conjunction, right? If only you had names for all the terms, right? If you are allowed infinitary conjunctions, right? For all x is actually conjunction over all possible x. There exists x is disjunction over all possible x, right? So for all introduction is like conjunction introduction. If you think of this as whole lot of premises, right? What is and introduction? Alpha, beta, alpha and beta. So this one actually stands for lots of premises. And similarly, and elimination looks like this for one of them, right? If you take the analog of that, this is disjunction introduction. Disjunction introduction looks like this. What should be disjunction elimination then? Remember, disjunction elimination has a special place in natural deduction. It's case analysis, right? Alpha or beta, if you have derived alpha or beta, from the assumption alpha you get something, from the assumption beta you get something, then you can derive that conclusion beta. So what does this suggest for there exists elimination? It's going to look like disjunction elimination, right? So, and this is how you do it. If I have derived there exists x alpha and by substituting some x, some c for x in alpha I have managed to derive beta, then I am allowed to derive beta. Take a few seconds and digest this. I hope this is clear. Now where should I, what is this? There is a side condition here. What is the side condition? All the nonsense about whatever I had for all introduction, it has to appear in there exists elimination, obviously, right? Where provided C does not occur in beta or in any undischarged assumption. Yeah, this is reasonable, right? This proof that you have got should not depend on C, right? You should not be using the fact that it's a particular C that is important. It's just something that you have picked, right? Remember, where C is arbitrary, that's what you want to say, right? The choice of C is arbitrary, therefore it suffices. The assumption that there exists x was enough to derive beta. This is what you are saying, right? The assumption of some bitness for x for alpha is enough to derive beta, right? That means let K be a witness, let C be a witness for alpha, from that I conclude beta, but the choice of C was arbitrary, therefore beta. This is how you write it in mathematical texts. And this is very important. In mathematical texts, you use this arbitrary business in two ways, right? When you want to write something, you want to prove something general, right? You say consider the statement, take some arbitrary element of whatever structure that I have got, I do the entire proof, and you say but the choice of that element was arbitrary, therefore it holds for all elements. This is one universal form in which you use. But you also use it in the existential form, right? Suppose this is true for some element, right? Well, consider a particular element, C. I do the entire work and I conclude beta and say but I did not use any property of the element, right? Haven't you seen proofs of this kind? Where you say there was no distinguished character of this particular element, therefore the assumption that there existed one was enough for me to conclude. The existence of the such an element is all that I used for concluding beta. So, okay, you just, anyway, this is all in words, you can check that this is sound, right? That means if gamma, if this is a consequence of gamma and this is a proof, then this is a consequence as well, right? And that's something that you can actually sit and do the proof of. Somebody else. Sorry, I didn't understand, Sujata, there is some comment.
So I just wanted to make this comment that in this alpha square bracket x by c third bracket, there should be a bracket outside, isn't it? Because it's an assumption. Or am I?
Oh, you are saying that this, yeah. Is that what you said? Yeah, sure. This is an assumption, exactly like I've written all these. Yeah, thanks. Is this an assumption, discharge? See, the thing is, the question that you are asking really is, when I apply this rule, am I discharging this assumption, right? Actually, you don't need to. You don't need to discharge the assumption, because as it happens, this is the one that you are discharging, right? I mean, but it's not an assumption in the natural reduction sense. Okay, none of these are assumptions in this sense. These are assumptions, but so you don't need to put this in. Okay, yeah. Anything else? Okay, I've got some examples, and well, these are all proofs. As usual, there will be some. Okay, here is something for the universal quantifier. Take some. Any question about the rule? So, shall I get rid of them? Okay, let me keep the universal. Okay, so here is the, what we want to do is something fairly obvious from for all x, not for all y, pxy implies qxy. We want to infer for all x I mean, of course, it's there exists y, but in whatever form you are given, you have to derive, right? So, okay. So, what is it that we want to derive? Remember, in natural reduction, you always start, or sequent calculus, you always start from the bottom. So, this is a goal, right? And you've got a for all x here. So, the only rule that you will apply is, the only way you could get to this is by a for all introduction rule. Yeah. I mean, this is how this goes, right? Because I want to derive this, and the primary connective that we are looking at is a universal quantifier, and that's below the line, so I have to use a for all introduction rule. So now, so I must come from some instance of this. So let me write PAY, and I'll have to now make sure as I go up that this A is something, A is not occurring here below, and I'll have to make sure that it's not occurring anywhere in any undischarged assumption, right? This is what it is about. Now this is of the negation form, so I need to use negation introduction, right? So that means from some I want to get a contradiction, and the contradiction I am going to use is this. It's, since it's sitting here, for all y PAY implies QAY, and I will have not for all y yeah, and then by negation introduction I can come here. Now here oh sorry, yeah, here I am directly given, so I can yeah, this is an assumption, and now I can use for all elimination, yeah, to get this. Is this step clear? This is directly given. I know that for all x alpha is here, therefore I can always substitute some element for it. If I substitute x by a, I get this, so this part is easy. What about this one? I have to somehow get this, okay. So this has to be a for all introduction rule, because there is a for all sitting here. So I'll throw in a PAB implies QAB, some substitution. Once again, as I move up, I have to make sure that, remember that B is not occurring anywhere below, so that's clear. And now I can use a, yeah, I'll do an implication introduction. So PAB has to move up. This is the problem with natural deduction. I never know how to plan this. Yeah. So somewhere I'll make an assumption PAB, and from that I have to get QAB. Yeah. So from PAB, so except that I'm going to do it in a, yeah. What I'll do, I'll get a not PAB, for which I can do an assumption for all y not PAY, from which I can get QAB. Yeah, oh, I didn't have to climb so much. Sorry about that. I can bring it down right here. Yeah. What is very nice is, now I have discharged both the assumptions here. Yeah. So PAB is discharged, as well as for all y not PAY is discharged. And there is no, so there is no discharged assumption undischarged assumption that is using A here. So this is important. So A can be used. Yeah, so this is a for all elimination, and this is a negation elimination. Yeah. So yeah, so as I'm doing this to show that you have to. Of course, I didn't do it precisely the way I showed you, right? Some part of it you do this way, some part of it you guess from top, ensure that it all meets up, and make sure that your proofs, the side conditions are met carefully, right? This is what you have to do, and you have to plan it out a little bit. And the plan really, as I said, you look at the form in which it is given, right? Given is for all x, not for all y, pxy implies qxy. And to prove is for all x, not for all y, not pxy, right? So as I said, the one part you can try to get directly by applying, which from the assumption directly you can get, and then you realize that somehow you were to get to not for all y not, right? So introduce a negation, I have to somehow get a contradiction from for all y not pay, right? And you have to make an assumption. When you have to make an assumption for it, you might as well assume PAB or for any particular constant as well, and get rid of it as you go down. Yeah. So yeah, at least is this proof clear? How it works? Any question related to that? So remember that PAB is discharged here, and this is discharged here. Yeah, and so that's important because when you are here, you have to make sure that when I do a for all introduction, I have to make sure that the element that I am using is not A is not there in the conclusion and not any undischarged assumption. So by the time when I am here, for instance, here I have to make sure that B is a constant that is not used below and that is not there in any undischarged assumption, and that is a point here because it's being discharged right here. Yeah, there is no undischarged assumption that is using it. Any other? So much of this is basically planning your discharging of assumptions a little carefully. That's all. Okay, now let me do one with the existential quantifiers. Any questions? Shall I move on? Okay. Yeah, I'm doing only examples that are fairly obvious. I'm not doing anything that is difficult in this, semantically at least. Okay, so here from, yeah, this is, there exists x, px and qx, and not there exists x, qx and rx, infer yeah, and it should be clear that this inference is sound. Okay, so I want there exists x, px, and therefore I need a there exists introduction. I have done this with there exists elimination. So that's a deadly. Okay, yeah. So this is a fairly complicated proof. Probably you can do a better proof, and you do it. I just want to show one, at least a proof that you would probably not think of. I don't know. Maybe you will, but I don't know. I wanted to show you a proof of this kind. So let's see. So I'm going to do this by there exists elimination. How do you think you can do it by there exists X elimination? So what I have is this. So there exists X QX and no, there exists X PX and QX. So this is one of the assumptions given, right? I start with there exists X PX and QX, and by making a substitution, right, I'm going to derive there exists X Px and not Rx by making a substitution, and so the substitution that I am going to make PA and QA, an assumption that will be discharged. Okay. Yeah. So let me work my way up. So the deal is that, remember this is the there exists elimination, right? If I've got there exists X alpha and I take alpha with some substitution, make this as an assumption, from that I can derive beta, then I'm allowed to arrive beta. This is the form of the exists elimination rule, right? There exists elimination is there exists X alpha, alpha with X replaced by C, beta, from that I can get beta. Yeah. So let's see. Maybe I should get rid of these. Okay. So first here this is from PA and not RA, and this is a straightforward there exists introduction. So how do I get PA and not RA? The only way is by AND introduction. I get PA and I get not RA. PA is by this assumption, and that's easy. Maybe I need a little more space. And this is from, sorry, and this is AND elimination. And here I want negation introduction for not RA. So I have I need to get some contradiction. So the contradiction that I use is not there exists X, QX and RX. This is an assumption that is given. So I get there exists X, QX and RX. So that will be my contradiction from our assumptions. So there exists X, QX and RX. This I am going to get by getting QA and RA. This is there exists introduction. Now QA I can derive from PA and QA. Remember, this is the assumption that I am discharging. That's AND elimination. And what about RA? That's an assumption that I can get rid of here. Yeah, I've gotten rid of it here. So that's it. So I have used both the assumptions, right? I mean, this is the assumption that I've used here, and this is the assumption that I've used here. Yeah. Okay. So as I said, this is only to demonstrate the way these proofs are built, and also to show that it's a fairly tricky business. In natural reduction when you go about, but at least you can use the formula structure to see how. And this also shows why with first order formulas are much harder to reason with than the propositional formulas that we were considering earlier. Mainly, and it is all to do with precisely the problem that we spent a lot of time semantically worrying about, namely about variable occurring free, a constant symbol used or not used in the assumptions, from which what you can conclude, etc. Okay. So any questions on this particular proof? As I said, of course, I've said this many times, formal proofs, if you watch somebody do it, you can only see, you can verify the steps, but it's hard to understand. You have to try out some things yourself and see how these things are used again and again before you get some intuition into this. Any questions? Okay. So then so that's pretty much it for natural reduction. Sequent calculus, the rules are very similar. Once you've seen the rules for natural reduction, sequent calculus of course is much more structured, so it's the rules almost pop out fairly straight. You don't have to do, you have very few assumptions that you have to write down. Sequent calculus, quantifier rules. I'm not going to write out all those left rules and right rules for all the connectives. We have seen them earlier. So here, what are the, so you have a for all left rule and for all right rule, and you have a there exists left rule and there exists right rule. So what is this going to look like? You have a gamma and delta. So you have to have some, so how does this go? Remember that in the sequent calculus, what is very nice is that there is no introduction and elimination, right? So the connective that you are looking for always appears below the line. So this is the form in which you have got. Yeah, and it's the form in which you appear on the right hand side. Oh, sorry. Yeah, there is only gamma. So yeah. So it's, this is a one of the most important things that you've got in sequent calculus, right? The logical rules have the subformula property. What is, you remember this? What is the subformula property? Anything that you've got, to derive something, you have to look at only subformulas of the conclusion formula, right? So this is one of the important characteristics of sequent calculus that I discussed earlier, and that's true in propositional logic and it's true in quantified logic as well. The only rule in the sequent calculus that does not have the subformula property is which one? Does anyone remember? Ananya is wanting to say something. Yes. Yes, Ananya? Sorry? The cut rule. The cut is the only one that doesn't have the subformula property, and that's why in propositional sequent calculus when I was talking about, and I highlighted the use of cut, and that's the one that can introduce inconsistency. It violates subformula property, so you look for cut elimination. This is one of the important reasons why proof structure comes out in sequent calculus. So you know that when you look at for all rule, left rule or right rule, it's always going to look like this. So what is going to be on top? Should be fairly easy. Well, this is, it doesn't matter whatever term, right? This is the generalization from constants or variables or whatever you've got, right? If that is your, remember left hand side is your assumptions, right? Assuming this, if you have got this, then you have got for all x alpha. And what about this one? Where provided x does not occur free in the conclusion. Yeah, this is the analog of saying that alpha implies for all x alpha where x has no free occurrence in alpha, except that now this is in the entire conclusion. X does not occur free in gamma, in for all x alpha, delta, right? That. So this is the difference now. And what would be the rules for the existential quantifier? What will be, there exists L and there exists R. Remember, there is no choice in the sequent calculus. It's strict duality, right? It's not like natural reduction where and introduction and or elimination look different, right? Conjunction introduction and disjunction elimination look different in natural reduction. In sequent calculus, whatever is the left rule for conjunction is the right rule for disjunction. Whatever is the right rule for conjunction is the left rule for disjunction, and so on, right? So there is absolutely no choice in sequent calculus. The moment you have written your for all right rule, the for all, the existential left rule has to be this. Where x has no free occurrence in the conclusion, and this if you have derived a conclusion alpha for some particular term, then you can derive the conclusion there exists x alpha from these assumptions. So, this is exactly how it has to be. So, this is in fact the more natural rule. This rule dictates the for all left rule, right? And this rule dictates the there exists x left rule. This is how sequent calculus, it's like a technology, right? It's like a machine. There is one part is driven by semantics, the other part by duality. Everything is structured exactly that way. That's why it's really neat once you understand how this thing is. And sequent calculus you can design, if you think of a new connective, you can design the logical rules for sequent calculus for that connective, it flows almost, right? Okay, so that this is sound should be pretty straightforward, right? Because the arguments for why this is sound is exactly like what we have talked about before, right? In a sequent, what does this mean? The conjunction on the left hand side implies the disjunction on the right hand side, that is a validity, right? So if the conjunction of all gamma implies the disjunction of alpha or delta, you want to show that the conjunction of the gamma implies there exists x alpha or delta. As I said, consider a model in which all of the left hand side is true. You want to show that one of the right hand side is true. If one of the delta is already true, we are done. Otherwise, you want to show that there exists x alpha is true. But it suffices to show that alpha holds for some particular witness, and that's it, right? So there exists alpha holds. This is pretty much the order of things in there. Okay. Any question on the formula? I hope the side conditions are clear, right? The side condition is, what is the side condition? It says that it should not be used, there should be no free occurrence of x anywhere in the conclusion. This bound occurrence is okay, right? There should be no free occurrence anywhere in the conclusion. That's it. And any is the idea clear? So, and the main point is that there is no business of making assumptions, discharging them, all that nonsense is not there, right? So it's a fairly clean system that you can work with. We don't have to worry about those scoping things that, remember in sequent calculus, natural reduction, one of the most difficult things to keep track of is, right, when you make assumptions, alpha and then beta, you have to discharge beta first and then alpha, right? So it's fairly important to make sure that so the scope is very careful, right? You can't cut across, right? And so all that is not there. In the sequent calculus, you ensure that. So we just leave that here and you can see. Okay, so let me give you a few examples again. So here is a proof. Use for the for all quantifier. So for instance, I want to show something fairly obvious, huh? For all y yeah. So I use the for all right rule for all x px. Yeah. Remember, y, I have to make sure that y has no free occurrence in the conclusion. Y has no free occurrence here and y has no free occurrence here. So this is important. Y will occur bound. Bound occurrence is okay, right? So this, the for all right rule is okay. And now I use the for all left rule, right? Yeah. And this is okay again for, so and this is axiom. Yeah. So some more. Here is one. Again, I'm only doing obvious inferences. I want to get for all x px. So once again, I can write why? Because going from here to here, there is no free occurrence of x anywhere in the conclusion. Yeah. Below the line, there is no free occurrence, and therefore I am allowed that. So I can, and this one, px and qx, I can use for all left, which is and this this is and left rule. Anyway, a list is the same as conjunction on the left hand side and a list is disjunction on the right hand side. So this is and left, or similarly you will have the or right rule, and this is X. So I'm also doing it to show you that how in sequent calculus the proof really flows. Okay, natural reduction, for all its naturalness, the choices can be quite horrible. In sequent calculus it's much more okay, maybe nothing is straightforward, but I guess it's really me showing my preference for it rather than anything else. Okay, so suppose I want to derive for all x alpha implies beta, from that where right, and this is the validity of this is you have seen this before. I mean, this was, I think, one of the first problems that I had given, that for all x alpha implies beta implies alpha implies for all x beta if x does not occur free in alpha, right. So we know there should be a proof of this. Let's do the proof. So once again I'm going to do implication right, and implication right will come for all x alpha implies beta alpha, from that if I can get for all x beta, right. How do I get an implication to the right? Assume to get alpha beta or whatever, gamma implies delta, assume gamma, show delta, then you can. This is the implication right rule in sequent calculus. So now this is fairly straightforward. For all x alpha implies beta alpha, I can get beta for all right, and verify the condition. The condition is clear because x has no free occurrence on the in the conclusion, and now I can do beta. This is for all left, and now I want implication left. Implication left I have to have both sides, and yeah, and this is both of them are X. Yeah, so this is, as I said, another straightforward one. Let me maybe do one with existential quantifier. Yeah. There exists x px or there exists x qx derives there exists x px or qx. Okay, so I want or to the left, so I have from there exists x px, I derive there exists x px or qx, and I have another one, there exists x qx, and let me do this side of the proof. This one is similar. I am not going to. One side of the proof I will do, and it will follow in the almost the same way. So, from Px I will try to derive there exists x, Px or Qx. This is the there exists left rule. Whenever you got something here, again there is no free occurrence of x below, right. For there exists L I have to again check. So, I will just write check, and now I want from Px or Qx. This is the there exists right rule. There exists right, there is no check, and anyway this is true, and this is R to the right and this is X. You are going to have a pretty much the same proof structure on this side also. So, the way the proof goes should be fairly clear, right, because you have got a disjunction in the assumptions. You have to show this separately for each of the cases, and in each of the cases you realize that there is a symmetry. Whatever I do for Px or Qx here, I can do a very similar thing from the assumption Qx, and once I have got this assumption, you want to somehow get rid of the quantifiers and see, and for getting rid of the quantifiers there exists L does the job. You just have to make sure that whatever variable that you are using has no free occurrence below, and that is the case, therefore I can do that, and once you have got this, it is completely straightforward. Okay. So, let me do a slightly different kind of example, because I should have done this with natural reduction also, I am sorry I forgot that. So, I am going to take up one where the formula that you are trying to derive is not valid. So, there should not be a proof, right. How do you check that that happens, right. So, let me try to prove there exists x Px and there exists x Qx. From this I will try to derive there exists x Px and Qx. This should not be possible, right. We know that this is not possible, right. You can always have there exists x Px and there exists x negation Px, but you can't have there exists x Px and negation Px, right. That you can't have a contradiction with an existential quantifier. So, this proof should not work, right. So, let us see how it goes, because I am trying to tell you that there is like a machine, no. In each case you can start doing it and derive a proof. So, what should happen in this? So, let us check it out. So, first you have an AND left, right. So, you must have, and this is the thing that comes for free, there exists x Px, there exists x Qx. From that I want, okay. Now, I have a there exists on the left hand side, it does not matter any one of them, let me pick Px, there exists x Qx, and this is the same right hand side. Now, I have a there exists left, and now I already have a problem. X is occurring free out here, right. So, I cannot have Px Qx here, so I must have Qy here, Px Qy, and there exists x. Is this clear? When I am applying the there exists L rule, right, when I am knocking off the existential quantifier, you could knock it off once, but not twice. Second time when you look at it, x is occurring free. So, you can't have x coming here, so you can only have some y, right. and now you're going to have a problem, right? Because I'm going to have now, if I do there exists right, I will get Px Qy yeah, and you won't get a single, and you are stuck, right? Right, and that's, for me at least, an illustration of how your you can't find a common instance, right? A single substitution that makes both the same, yeah. And so this is the sort of thing that you, from this there is no way to get, I'm sorry, you want Px and Qx, and there is no hope of, yeah, providing here, yeah. So there is no way from Px and Qy to get Px and Qx, and so sequent calculus, what is very nice is that it keeps pushing finally till you get the atomic formulas where the axioms hold, right? And at that level you will find your inconsistencies. Until then you keep manufacturing lots of variables, new terms, whatever, but that's where it stops. Okay, so as I said, this is an illustration. I'm not doing too much of proof theory, but at least one should have some insight into how these proof systems work, right? So, so last time we talked about, not last time, whenever we talked about natural reduction and sequent calculus for propositional formulas, very similar ideas lift for quantifiers, and the completeness we did for the Hilbert system and used the derivability of the Hilbert axioms, the mutual derivability, right? The Hilbert axioms are derivable in the natural reduction, and natural reduction one rules are derivable in the secant calculus, and the other way about, and to show that they are all equivalent. But like I said, for like we did in the case of propositional calculus, this is not how theorem provers work, because you don't know which, there is just too much non-determinism in deciding which terms that you can make use of, and it is for this that I introduced resolution in the context of propositional calculus, and I talked about the DPLL procedure, the whatever Davis-Putnam, Logeland, Lohmann, that procedure, and then told you also how SAT solvers use those rules. Now, I'm not going to do a lot of resolution, but at least to get some understanding of how these things work. Remember, Davis-Putnam introduced all this for quantifiers, right? And there is also a very important, in the transition from going from formulas to clauses in the clausal form, and then doing resolution, you use a very important thing for, in the case of first order logic, and this is the idea of scolomization. And scolomization is something sufficiently important for us to learn. So I'm going to talk about scolomization. So we'll use these column functions to go from first order formulas to clauses in the clausal form, right? Clausal form we were doing with CNF, right? The conjunctive normal form, and where you have a bunch of conjunctions, and each conjunct is a bunch of disjunction, right? It's a conjunction over disjunctions, right? And so that's the clausal form, but that's a propositional form, right? And finally you have literals. Now you're going to have literals here as well. That means you have atomic formulas or negations of atomic formulas, and you can have disjunctions of them, and you take conjunctions of them. But what happens to quantifiers? Scolomization is a way of getting rid of quantifiers. So scolomization, I usually call it as a program for reducing first order logic to propositional logic. Well, not quite propositional logic, because what do you do with all the symbols? This is really what we call ZOL, the zeroth order logic, right? Where you have the syntax of constants, terms, variables, function symbols, right? Predicate symbols, equality, all of these, but no quantifiers, right? You have everything else. So that is Zoll, and that's what we do. So Scholemization is the process of doing that. How do you do this? And it's a very interesting and beautiful idea. Due to Scholem, of course. Why else will you call it Scholemization? Yeah. So first thing is take a formula in negation normal form. What does negation normal form mean? Push negations all the way inside. And that's very easy to do, right? We know what is that. I mean, what is not of alpha and beta? Not alpha or not beta. So you can push negation into conjunction, disjunction. Not of alpha implies beta is alpha and not beta. Not of for all x alpha is there exists x not alpha. Not of there exists x alpha is for all x not alpha, right? So you can always push negations inside. So so by which I mean we assume that negations occur only in front of atomic formulas, right? So you have T1 equals T2, so the syntax is T1 equals T2, T1 not equals T2, P T1 through Tm, not P31 through Tm, and then disjunction, conjunction, implication, if you like. And why have implication, right? We want it in clausal form, so it's enough to have only conjunctions and disjunction. And then you have for all x, there exists x. These are the only possibilities. Now, consider any occurrence of the existential quantifier. If your formula has an existential quantifier, it's going to look like some for all x1, then for all x2, let me go on, and then some for all xk, and then there exists y alpha. So this is the leftmost existential quantifier. Yeah, with k greater than or equal to 0. Yeah, that means that existential quantifier, if the formula has an existential quantifier at all, look at the leftmost fellow. Before that, look at all the universal quantifiers there are. There may be none, right? So now the idea is, in this, let f be a k function symbol not used in the formula. So let me call this formula beta, where we are beginning. Yeah, take a new function symbol not used anywhere in the formula and replace now. So beta prime is the formula, same thing for all x1, for all xk, and alpha with y replaced by f of x1 through xk. Why? Because this existential quantifier y depends presumably on all these x1 to xk. So replace it by f of x1 to xk. So that's the idea. So and now if k equal to 0, then the formula beta prime that you are looking at is simply alpha with x replaced by some constant symbol c. C is a constant symbol not used in alpha. Yeah. If there is nothing else to the left of the existential quantifier, not used in beta. God knows what context this existential quantifier is in. Yeah. So this is the idea of Scholemization. Look for the existential quantifier. If if it doesn't depend on any universal quantifier at all, replace y by some new constant symbol c. This is the idea of witness fulfillment, right? There exists y alpha is replaced by y, yeah? This is not x. Yeah. So for the existential quantifier, you are providing a witness. What is the witness? Some new symbol. This is what we have been talking about, right, all along. You can't do it in general because this fellow may be dependent on whatever is the universal quantifiers that you have seen before. In that case, you choose a function symbol. So existential quantifiers are eliminated using constants and function symbols. That's the deal, right? Well, you got rid of one existential quantifier. Apply repeatedly. What will happen? At the end of this exercise, you do all of this and you will get a universal formula. I have written for all x bar to say that you will have only universal quantifiers in the formula, right? Then drop the universal quantifiers. So after repeat until all there exists are eliminated. By this process, you can eliminate all the existential quantifiers. Now you have only universal quantifiers in the formula. Simply drop the universal quantifiers. Now you will have a Zoll formula, right? So this is a Zoll formula. Because it will have free variables, it will have all free variables are now implicitly universally quantified. That is the idea, right? And that's it. It's a very simple and beautiful process, and by which you can, but what have you done in the process, right? You started with the formula beta and you have come up with the formula beta prime. What is the relation between the two? Well, take a very simple formula. Now this is a valid formula. Can you see that it's valid? There exists x, PA implies PX. I mean, okay, I'm going to assume that I'll have only non-empty domains, so that yeah, from now on. Empty domain creates some hassle in by the way, in natural deduction, secant calculus, when I'm doing proofs or when I'm doing resolution, I'll always assume non-empty domain. Empty domain is a pain that needs to be taken care of separately, so let's just make that assumption. Yeah. So now this one is perfectly fine, right? You have some element, once you have A is true, of course, there exists XPX is also true, right? Now when I do Skolemize, what will I get? I will get PA implies PB. This is of course not valid, right? Just because P is true for A, it doesn't mean that P is true for B as well, right? So Skolemization does not preserve validity. What it does, it preserves satisfiability. And this is very important to keep in mind. Skolemization is a very natural process. What it preserves is not validity, but consistency. This is how you would say satisfiability. Yeah. So what it means is that if you start with the formula beta and apply Skolemization, you get a formula beta prime such that beta is satisfiable if and only if beta prime is satisfiable, right? But it's not about truth in all models, in about a particular model. And that it preserves satisfiability should be obvious, right? Why? Suppose there is a model M, it satisfies, there exists, suppose it satisfies for all x there exists y alpha. Then what does it mean? Then for every element of the domain, right, such that you choose, right, x is assigned d, there exists some d prime belonging to d such that m with x assigned to d, y assigned to d prime satisfy alpha. And of course, therefore, this if and only if for some function d from d to d, for some f function f d to d, if d belonging to d, m with x, y with f d satisfies alpha. Yeah. So that's why if for all x there exists y alpha is satisfied, then this column form alpha prime is satisfied as well. So this is the idea. So it preserves satisfiability, but it does not preserve validity. To move over, you may have to go to a different model, right? Because remember that there are all kinds of functions possible. This is that for some function, right? Now that function, you can choose many different functions that from d to d that will make this true, and each of this will give you one model, right? So from the original model that you've gone to different. That's exactly what happens here. This is from the model that made it true, you moved to a different model, right? So there are lots of different models, and so Skolemization says that if there is a model for that, there is a model for this, right? So it preserves. But what is very nice is that if you are going to do DPLL, right, you are really looking for a decision procedure for satisfiability. So therefore, there is no problem. In the case of resolution, where you want to show validity, right, of a formula, how do you do it? You do by refutation. You deny that is true and build a counter model. So again, you are preserving unsatisfiability. So no problem. So you will see that resolution. You start with your formula, do Skolemization, you get into a Zoll formula, and then turn it into clausal form and apply resolution. Right? The only thing is, what do you do with the free variables? So then that's the only thing that's left, and that's what unification is about. So we'll go over that next time, right? So it's a very simple proof procedure. What is very nice about resolution is that there is only one rule, right? Unlike all these Hilbert system, there are lots of axioms and small number of rules. Natural reduction sequent calculus, there is only one axiom but lots of rules. Resolution brings it all down to one thing, only one rule, apply repeatedly, that's all, right? And therefore that's what theorem provers like to do, and in fact it gives you a programming paradigm as well, right? It's one. So what is very nice is that now you can start looking at logic as a programming language, and the resolution engine becomes a way of executing programs. So this is the idea of logic programming. So not going to do much into all these things, but at least we should have some idea of how Skolemization gives you a very powerful way of executing logic specifications. Okay, so that's what we'll see next time.